Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, ladies and gentlemen. First of all, I would like to introduce our team, Mr. Masmehra PhD, and then myself. My name is Dia Krishna. The title of this paper is Numerical Simulation to Determine the Effectiveness of groynes and breakwaters as Protective Structures for Gandoria Beach, Pariaman City. First is introduction. Gandoria Beach is a tourist beach located in Pariaman City. Usually, in normal wave condition, the beach is well protected. But when there was a stormy wave or high spring tide, then the abrasion and erosion process occurred. We can see in this figure, sometimes after the stormy wave, temporary treatment needed to prevent a further damage to the beach. The previous research by Ondara et al. Showed that the shore protection that have been built along Gandoria Beach are a series of groynes, and within a few years these buildings have changed the hydrodynamic pattern of the waters, but at present conditions appear to be ineffective in reducing the rate of abrasion. The objective from the study is to determine the effectiveness of groynes and breakwaters by numerical simulation. The more effective shore structures will be identified by the resulting bathymetry. Coastal modeling system. The CMS wave is a steady module, while the CMS flow is an unsteady module. These two modules are different, but they are integrated each other as a single unit in the coastal modeling system. First is data collection. Bathymetry raw data were collected from Bathymetry Nasional. Wind data for 10 years of observation were collected from BMKG Minangkabau. Tide data for a period of 20 days were obtained from Badan Informasi dan Geospasial. The second is data processing. Bathymetry raw data are processed using ArcGIS to obtain bathymetric data. Wind data are processed in two stages. Determination of the simulation domain for the coastal modeling system. Numerical setup for CMS wave and CMS flow using bathymetry as the basic data, and then followed by making a grid, inputting boundary conditions and other parameter data. Figure 2 is the parent domain and child domain. Basically, the simulation is carried out in two stages. The first is simulate waves without interaction with currents or CMS wave only on the parent domain. And the second is simulate with current interaction on a child domain by coupling the two modules, CMS wave and CMS flow. The first stage simulation with CMS wave on parent domain. So why do we need to simulate in two stages or two domains? Because the bathymetry at the research site is relatively complex. There are three small islands which are quite influential on the wave diffraction process. CMS wave can cover a large area, but CMS flow version 375 is only intended for small domains and cannot cover domains that are too large for small grid cells. The simulation in the parent domain is carried out in two conditions, namely normal waves and storm waves, and we only use CMS wave here. The purpose is to get a wave output from the parent domain to be forwarded as a wave input in the child domain. The second stage of simulation with coupling CMS wave and CMS flow on the child domain. The focus of our research is on the child domain, where groynes and breakwaters are located. We used both CMS wave and CMS flow here, with the coupling process to pass the data in two directions. Simulations on the child domain are carried out in 6 scenarios. This is the figure of coupling process. In child domain, simulations of morphological change due to the interaction of waves and current were carried out for 20 days, for each scenario with a step time interval of 6 hours for wave simulation. Result and discussion. First is wind wave generation. From the windrows diagram, we know that the dominant wind and also waves were from the west. And this is the final result of wind wave generation using the SMP procedure. First stage simulation, CMS wave only on parent domain. The red line is the location of CMS wave output that will be passed as boundary conditions for the simulation input in the child domain. Second stage simulation, coupling CMS wave and CMS flow on child domain. The effectiveness of the shore protection structure can be seen based on the bathymetry that is formed as a simulation output. Figure 9 is the existing morphology: A. Condition without structure, B. With addition of groynes, and C. With addition of breakwaters. Figure 10 is the morphological change after 20 days of simulation with normal wave condition. Figure 11 is the morphological change after 20 days of simulation with stormy wave condition. We will identify the more effective shore structures by the resulting bathymetry. In normal wave condition, breakwaters give the best result as shore protection because in normal wave, sediment transport is influenced mostly by wave and then current. But in stormy wave condition, the simulation showed an anomaly that during a storm, the wave height and its energy towards the shore decrease because some of the waves have broken further from the shoreline. Current forces at very high speed are the dominant cause of erosion process along the near shore. So in stormy wave, the role of groynes is more dominant than the breakwater because groynes function well to hold sediment transport along the near shore. That's all our presentation. Thank you very much for your attention. Wassalamualaikum warahmatullahi wabarakatuh.